Hello everyone, and welcome to the CAD Engineering Drawing Series. Whether you are a secondary student or a technical college trainee, this series is designed to bridge the gap between knowing the software and thinking like an engineer. In this course, we aren't just clicking buttons in CAD, we are learning how to produce documents that can build the world. Before we dive into our three major projects, the nut and bolt assembly, the wood lathe tool rest, and the lever subassembly, we must master the grammar of engineering, standards and sectioning. These are the rules that ensure a drawing made here in Malawi, or anywhere in the world, can be read and manufactured perfectly by anyone else. It must be easy to read at a glance. Accurate, it must represent the exact geometry. Standardized, it must follow established rules, like ISO or BS standards. In this series, we use CAD because it gives us a level of precision that manual drawing cannot match. But remember, CAD is a tool, not the brain. The software won't tell you if your drawing is illegal, according to engineering standards. That is what I am here to teach you. In this section, we will define exactly what engineering terms are and why they are the foundation of any professional drawing. We're going to look at the most common terms you'll encounter in this series so that when you see a label on a drawing, you know exactly what it means for the manufacturer. Engineering terms are the specialized vocabulary used to describe the physical features, material properties, and manufacturing processes of a component. To ensure precision, engineers avoid vague descriptions like rounded edge or slanted cut, using instead precise technical terms such as fillet or chamfer. This terminology ensures that everyone, from the designer to the machinist, understands exactly how the part should be made. To save space and maintain clarity on a drawing sheet, these terms are often abbreviated. For example, across flats is written as A, F, and figure becomes Fig. Here are some common engineering terms and the corresponding abbreviations that we will use throughout this series. Now that we understand the terminology, we need to talk about engineering conventions. While terms give us the names of features, conventions give us the rules for how to draw them efficiently. So, what exactly is an engineering convention? Think of it as a professional shorthand. In a perfect world, you might want to draw every microscopic detail of a part, but in a professional workshop, that is often a waste of time. Instead of drawing the literal reality, we use a representation sketch. Let's look at some practical examples of these conventions. As you'll see, we replace complex physical details with simplified, standardized sketches to keep our drawings clean and professional. Now, let's move into one of the most powerful tools in engineering drawing, sectioning. Up until now, we've looked at external views. But as an engineer, you often need to show what is happening inside a component. Perhaps there are hidden chambers, complex bores, or internal ribs. If we relied only on hidden, dashed, lines to show these, the drawing would quickly become an unreadable mess of overlapping dashes. Sectioning is our solution. Imagine taking a saw and cutting the object directly through its center. We then remove the front portion and look directly at the exposed internal face. This allows us to use solid, continuous lines for internal features, making the drawing instantly clear. When we create a section, we use two key indicators. The cutting plane line, this is a thick, dashed and dotted line that shows exactly where the cut was made. It has arrows at the ends to show the direction our eyes are looking. Hatching, we apply slanted lines, called hatching, to the areas where the saw actually touched solid material. If the saw passed through a hollow hole, we leave that area blank. Here is an example of sectioning. The cutting plane R on the top view of the lever subassembly has instructed us to cut it there and show the inside in the front elevation. Consider this example of the lever subassembly. The cutting plane line AA, indicated on the plan, top view, dictates exactly where the component is divided. The resulting sectional front elevation then reveals the internal assembly details that were previously hidden, providing a clear view of how the lever and pin interact. Before we move into the CAD demonstration, we must master the rules of hatching. Hatching is how we tell the machinist, this is solid metal. If you hatch incorrectly, the part cannot be manufactured. Follow these 4 core rules to ensure your drawings are professional. 1. The hatching style. Line weight, always use thin, continuous lines. Spacing, lines must be evenly spaced. Angle, hatching is almost always drawn at 45 degrees. 2. Assembly clarity. In an assembly, different parts must have different hatching directions. If the main body is hatched at 45 degrees, the part touching it should be at 135 degrees. This makes it clear where one part ends and another begins. 3. The solid material rule. Only hatch where the cutting plane actually touches solid material. If the cut passes through a hole or a void, leave it empty. Hatching a hole is a major error. It tells the machinist the hole doesn't exist. 4. The no hatch zone, critical. There are certain standard parts we never hatch, even if we cut right through them. These include fasteners, bolts, nuts, pins, and keys. Support features, webs and ribs, when cut longitudinally. Moving parts, shafts, gear teeth, and spindles. Leaving these parts solid makes the drawing much easier to read. Remember, if it's a standard part or a fastener, do not hatch it. Here is a demonstration of sectioning. When drawing a nut in CAD, we must follow specific engineering standards. Please note that the proportions and conventions we are using here apply specifically to metric, ISO, nuts only. When drawing a bolt, we follow a similar set of standardized proportions. Note that these conventions apply specifically to metric, ISO, bolts. Using these ratios ensures that your CAD models remain consistent with international engineering standards. Now, I will demonstrate how to draw the projection symbol. Take a moment to look at the diagram in the bottom right corner of your screen. This shows the mandatory standards and proportions required. For this exercise, I am drawing the first angle orthographic projection symbol. Notice how the small circle and the truncated cone are aligned to signify this specific layout. That concludes our introduction to the standards, terms, and conventions of engineering drawing. Understanding these rules is the first step toward becoming a professional designer. Now, we are ready to put this theory into practice. Here is our roadmap for the upcoming lessons in this course. Lesson 1, the nut and bolt assembly. We start with the basics of fastener construction, focusing on thread conventions and correct metric proportions. Lesson 2, wood lathe tool rest and holder. In this lesson, we move on to a more complex assembly, looking at how different components fit together and how to represent varied materials. Lesson 3, the lever sub-assembly. Finally, we will tackle a complete sub-assembly, applying our knowledge of sectioning and advanced hatching rules to show internal mechanics. For every lesson, a link is provided to download a comprehensive resource PDF. Each pack contains the practice exercise, the completed solution for you to check your work, and a reference sheet of the engineering standards used in that specific session. Let's get started. I'll see you in Lesson 1 as we begin the nut and bolt assembly.